And then I need to go to sound settings. No, I don't want that. I want the volume mixer. Why doesn't it see Chrome? What the hell? I assume that's Chrome. Oh, there it is. Alright, hopefully the audio is not too loud. I can pull that back a bit on stream. Hey, what up? Thanks for joining us. Little Nugget with barbecue sauce. What a great name. The music is probably still too loud, I think. Alright, so it turns out I can play this music, and it doesn't get copyright striked, because Savage is pretty cool, so... That's a benefit to why I'm choosing to play this music. Okay, so the last stream kind of died, because... Oh, fuck, where is the current one stream? Oh, there it is. Yeah, the last stream kind of died because I had my bitrate up set way too high, and then it died like 18 minutes into the stream, and then I just kept going. Oh man, I'm kind of glad that I kept going though, because there was a lot of stupidity I had to get rid of. Like in the assembler I was working on, like I was having so many problems, and it took me like an hour to do something that should have taken me like 15 minutes. So I'm kind of glad that wasn't caught on stream. Am I still live? Copy video URL. Sorry, we might get some feedback here if I don't mute this. Alright, yeah, it says I'm... YouTube says I'm live. Let's see how low latency this is, because I set it for low latency. Oh, it's not that low latency. Jesus Christ. Alright, anyway, I should share the stream link, right? Try to get some views on here. That's it. Doesn't go in announcements. Fuck. Whoops. It goes here. I didn't change the thumbnail yet. I'll change the thumbnail after I'm done live streaming. Update it with something more accurate. Where else can I post this? I post some redstone in the random. Spam probably here. Live now. Post in top red. I think that's all the servers I can milk for views right now. Alright. Cool. So I don't know how long I'm going to be on, but we'll at least get some shit done here. Or at least go over what I've done. So I already made it so that it ran Fibonacci through like an instruction programmed in the ROM here. And I got that instruction written through my assembler. That's what I worked on last stream that kind of ended abruptly, and I just kept going without noticing. So, but what I changed now is I ended up making it so instead of just having 32 registers, which is 5 bits per register address, so 5 bits for the destination, 5 bits for source 1, 5 bits for source 2. Instead of 5 bits, now it's 6 bits. And yeah, basically the registers doubled. So if I open up the circuit, I have built a way to take a multiplication result that's always, so whenever you source A and B, whatever's sourced on the A and B buses will both go to, if I look here, will both go to the multiplier and the arithmetic logic unit, and then it'll just take, it'll either just allow the arithmetic logic unit to write back into the GPR's data in, or the multiplier will always be seen at the multiplier data in. So what I'm going to do to handle this is I'm going to have an extra set of registers that only hold the low and high bits of the multiplication result, because when you do multiplication on two 32-bit values, you get a 64-bit value, so you need to store that back. Ah shit, So since you got to store that back, you need to have 32 bits out for the top, for the high bit word, and 32 bits for the low word. And I have 5 addresses here. And what happens is when you write data in, you have to zero align it. So the value for the registers has to be greater than 31, because 0 through 31 is just the general purpose registers here. So if the address that you're writing to is greater than 31 and it's even, then you're able to write that to the multiplication input, because then what it does is on the even word it puts the low 32 bits, and on the high word it puts the top 32 bits. And that's how you write to, so that's why it has to be zero line. So if you're at address 32, that 32, the low byte word bytes here, and 31, the high right, or 33, sorry, the high byte writes here. High word byte writes here. Jesus Christ. That's a fucking tongue twister. They're words because there's 32 bits a pop, and you have a high one and a low one. So I just always add 1 to the result of the register write address. That's what that means. Multiplier register write address. And then this is like multiplier register source 1, source 2, register write, source 1, source 2, and I just copied some of the names off that. And this then generates those control signals to allow which one through to get onto the bus. So I tested that, and that works. God damn it. Okay. So that was inside this box. And then what you can do is you can then enable the multiplier write enable, or the general purpose registers write enable, with the instruction. So that's like another bounds on it. So like the assembler, if it fucks up, it has like a little bit of checking there. It would only allow the multiplier registers to get written on the multiplier instruction, and only let the general purpose registers get written on the arithmetic, logic, and shift instructions. But some other instructions are going to have to use those registers, so I'll have to enable them as well as we go through this. For instance, actually I need to do that with set less than and set less than unsigned. I have to make that also go into that, which is easy as doing this. I hate how they like space that input out. Alright, because what set less than and set less than unsigned does is it puts a 1 in the registered write address if the condition is true. So it comes over here and it looks for a condition. SLT, SLTU, control instruction. Comes over here and says we're going to take whatever's true here. So whatever you load on the bus is if A is less than B, and then you can check for either signed or unsigned. So, oh, that's one thing. Oh, no, that's fine. So this is the unsigned flag and this is the signed flag, so depending on which one you check for through this decoder here, it will return a 1 on this bus if it's true, and then get written back into the result from the address given by A and B in the instruction here. Okay, so inside the ALU, yeah, it was just this simple logic. All I did is took the arithmetic select, logic select, and shift select muxes, brought them in here, decoded each flag, and then, you know, that's what it then will do. It will do either one of those operations on A and B. And that's why the multiplier is parallel to the ALU, because it gives out a 64-bit result from two 32-bit inputs, whereas this gets a 32-bit result from two 32-bit inputs. So you get like bus doubling with here, so like that's why it has its own separate port on there. So that's the only 64-bit bus on the thing. Everything else is 32 bits or less. Okay, so what I need to do now to actually test this, now that see if this even works still to this point, is okay, fuck, and I forgot to mention yeah, so I was fucking around and like let's say I wanted to do DMA. This has to be updated still, so I'm gonna end up taking the circuit out and using it later. What I'd like to be able to do is let I/O ports, or let devices attached to the computer through a port be able to have direct memory access. So like they don't have to use two ports to communicate with the CPU. They don't have to go, here's the memory access I want and here's the data, and then that goes to a port and the CPU then pulls the port and goes, okay, cool, does something with it, and then sends a flag back out to the device saying, okay, give me another one. That would be very slow. What this does instead is it says the I/O device has access to the RAM bus during the DMA access, we'll call it. So the DMA controller takes control of the RAM bus, and what I'm thinking about doing is just halting the CPU. So like it receives clocks, it just won't increment it through the program counter. So it'll just hold state basically. Because right now it's just single cycle, so that's the easy way. And I'll just let the DMA access have control of the RAM, because this way the CPU is not running while it's, and there's no way to execute a load word or write store word instruction while the DMA is going this way. I can make it so that it doesn't have to halt, and then it just prevents, or make it on the programmer to know like not to use those. But I don't want to do that. I'll just halt the CPU, let the DMA have control for the time that it needs, for the cycle count that it requests, and then we're good to go. So the way the CPU is going to do it is there's going to be 8 input ports and 8 output ports. The DMA system is going to need to use 3 output ports, and it's going to have to grab the iteration amount, so how many times to count, and then like the amount to count by, and then the offset to start from. So like let's say you want to count bytes from address 3F in memory. You put the offset as 3F, you take the amount to count by as 1 because you're counting 1 byte at a time, and the iteration account amount, how many times do you want to read the buffer, how many times do you want the I/O device to actually, how many RAM addresses are you trying to reserve for this I/O device, like what are they going to use, that's the iteration amount. And so on those 3 ports, what will then you write to those 3 ports, and then you run a DMA store or load, depending on what you want, whether you want access to the DMA device or the DMA device wants access to your RAM. And then from there, it will then use the DMA ID that's included in the load DMA or store DMA instruction. So like there's a 32-bit immediate provided with the instruction. So the DMA ID can be a 32-bit literal, and the load DMA or store DMA picks the device ID. So since I just have 0 through 15 devices, because I just, it's already massive at this size. Like look at all the in and outs here. It's easy to expand it, but I don't think I need any more DMA devices for now. So it's really just only 4 bits, even though it's got a whole 32-bit value like available to it. So it could have a lot of I/O devices technically. The issue is I only have 2 to the 24 words of RAM, and the RAM is byte addressed. So I really only have 2 to the 24 bytes of RAM, and then I really have 2 to the 22 words, and because each word is 4 bytes. So that's all I can work with here, but I figure that's still enough to like have some part of the RAM be a memory map for the screen, and then have the DMA device access that part of the memory. So what I'll do is on the DMA device hooked up to it that's, controlling screen, I'll have the offset for where it writes memory applied to as the base for the screen buffer in RAM. And then tell it like, there's, it's 1,000 pixels by 1,024 by 1,024, and then just say count until you overflow past 1,024 times 1,024, and it's a 32-bit count value, so it's not going to overflow. If I pull up calc. 1024 times 1024, yeah, is 1,000,000, and I have 32 bits to work with here. Which if I go to binary and clear this shit, alright, no, we'll go to hex. Sorry, 1, 4, 8, 16, 32. So we have 4 million to go with, or 4 billion, and the other number that we had was 1 million. Yeah, was that? Well, plus 1, so really 1, 0, 0, whatever. So with our 32-bit value, we'll be able to easily fit a whole frame buffer. Well, I guess it's 2 to the 24 shit. And yeah, that's gonna be, the frame buffer could take up most of memory. Okay, maybe what I'll do is oh no, that's fine. What we could do is just have the frame buffer be an external device instead of being internal to the memory, and then the CPU can issue a DMA access to the RAM to write whatever it wants to that. That would be even better. Yeah, this way you don't need the full thing. Okay, that might work instead. Either way, we could work through it. Or I could double the amount of RAM by putting two of them next to each other. I may end up doing that, but that only gives me 2 to the 25 bits. Which I guess still does double it, so whatever. This is bothering me. Okay. So and you can see like I hooked up a terminal and a keyboard. And the clock comes over here, and then the DMA control. I need more outputs over here to control the enables on this shit. So for now, we're just gonna eat it. And here's the RAM that we're gonna be using. The RAM is built into the default functions in digital, which is pretty cool. You can go over here to components, library, RAMs, and it's right there. It's this guy, RAM 32-bit. And you can give it how many like address bits and whatnot you want. So like we're gonna have address bits equal to 24. Okay. And yeah, we can open up the circuit. And now that we define that, it knows how many bits and all that shit because it's using generic identities to do all this. So this is the built-in one, and you can see here's just a mux. It's just taking in different 4-bit values and splitting them out and sign extending some. And over here is like the same thing. So this was just the built-in circuit, so it's just real nice to use this. And now this doesn't force you to zero align the way they built this, which is cool. Like you don't have to have bytes. Well, bytes don't need alignment. Halves would need 0 alignment, and then words would need 00 alignment, aka multiples of 2 and then multiples of 4. But here, like you can do that, but like not have them 0 aligned, if that makes sense. You don't have to have the zeros right shifted. So like that's neat, but also kind of odd, you know. So like I'm forcing everything to be byte aligned and word aligned and half aligned, like by default. Okay. So yeah, what I want to do is pull up the assembler, and I want to get it so that because I haven't updated the assembler to be the new instruction width where I added 3 bits to each one of these. So that's what I'm going to do right now. We're going to pull up PyCharm, which I don't have up. Okay, wow. Okay. So here's like some hard-coded Fibonacci, where it just takes like register 1 is R1, register 2 is R2, register 3 is R3, and immediate is equal to like a 1-bit value of like a 32. This is all in hex, so that's like a 32-bit value, but it's just got a value 1 in it. So what I'm saying is, you know, set R2 equal to 0, then reg1 gets reg2 plus the immediate, then reg1 gets reg1 plus reg2, then reg2 gets reg1 plus reg2, yada yada yada, and just did that a few times until it would overflow on, I think it even overflows like right up to this instruction here on 32-bit value. Anyway, that's just it hard-coded, so I want to be able to still take this code but have it output correctly for the current design where it has bigger immediate like registers. So the first thing I gotta do, which is kind of sucky, You see how like registers here, I had to define all of them. So we're gonna basically do this and copy and paste. Cool. Okay, so now what we want to do is, can I do it from a highlighting? Control F. How do I find and replace? No, I just want to do it in my selection. Is there a way to do that just in my selection where I could just select here and replace only in there? Whatever, that sucks. Alright, so we'll call that M0, M1. So really, remember, in the multiplication, it takes 2 registers to hold 1 result. So even though it looks like I have 32 multiplication registers, I do, but I don't because I really only have 16 because each one requires a low and a high. But this also is, I think, a better implementation than what MIPS does, because MIPS only uses a low-high register, and then you need a separate instruction. Oh shit. Then you need a separate instruction to do multiplication, whereas here the multiplication is being done all the time in parallel, and then you could just choose to use that result by selecting a register that lies within the result range for the the multiplications. So like it looks like I'm just going to leave that here, but I really just need to add a 32 to all these values. So this becomes 30. Wow, this becomes 32, 33. This is going to suck still. 34. Fuck, I just skipped 41. If I knew how to do like, what the fuck is it, Vim? I'm sure Vim could easily edit these out really quick if you knew what the fuck you were doing. Problem is I don't, so this is still quicker than engineering another solution to not do this. Like we only got like what, 64 more, or 14 more to go. Wow. 51. Four more. 1, 2, 3. I guess that was easier. Okay. Wow. What the fuck did I do here? Oh yeah, 60. I'm dumb. 1, 2, and 3. Okay, are we still live? It didn't cut out yet? Okay, cool, it didn't cut out. So now we've defined our registers, so now we can actually use the multiplication if we want. Put a comma there. That one doesn't need a comma because it's at the end. Cool, okay. God damn. Okay, so now we can use registers M0 through M31. Now, R0 in my design is forced to be 0, but the register system would allow you to write to 0. I checked it, so because they give you like a dual read register system. So I force it to 0 because I want a 0 register at R0. But then none of the other ones are aligned at 0, and that's good because M0 here, we need that to be aligned at 0 so that we could write the low word there and the high word there of the multiplication result. So I'll go ahead and save this. Now another thing that we need to do is actually go in and edit how large these values are. So at the bottom here, when it's done assembling all this bullshit, it comes down here and it puts it all next to each other as like an instruction. And the way it works is it takes this function xlength, which tells you how many bits, what you're trying to convert to that amount of bits, and whether or not the value that's in here is supposed to be signed or not. So the only thing that we changed is the amount of bits in RD. We made that 6. RS1 we made 6, and RS2 we made 6. And the immediate we have is 32, and of course we could put in a negative number, like the immediate can be negative F, and then it would know to make that negative 15 there as the right value, and it would convert that properly. So now I updated this. Now it should work for the add instruction, because that's the only instruction I have actually doing anything right now. So if we look at the add instruction, the add instruction says if the 0th argument of the input is add, then if the length of the instruction or of those arguments is not equal to 4, return all zeros. Basically, I'm saying like the length of the instruction has to include an add, a destination, a source 1, and a source 2. That's 4 things. Hey, what up, guys? What up, implicit? So because it needs to include 4 things, if it doesn't, you know, how's it going to know what to do? So it's going to get out of there and throw an error. Or it should throw an error, but I don't have it throwing one. Then what I'm doing is I'm saying if it comes in, if an add instruction comes in, then the opcode for add is 0, and the select position, the select is a 3-bit number, so it's 0 through 7. The select value has to be 1. So if you select 1 and 0, or if you put in add, then it's going to put these things out on the opcode and select buses. It's going to take the first argument that comes after add, which is the destination register, and write it as RD. It's going to take the second one, which is source 1, and write it as source 1. Then it's going to check if the third argument is an immediate or if it's a register by checking if it starts with any of these values. If it does, then it will convert that value to an integer and send it as the immediate. If it's not, it'll just know that, and then it sets RS2 is equal to 0 as a 0 register. Else RS2 becomes the third value, and you have to look up the registers for that to see what register it is. And then immediate gets 0. So since RS2 is 0 and immediate's being used, or immediate's being used isn't used and RS2 is being used, then that's the implicit XOR there, and I don't need to put a mux on the buses. I can just OR the buses together, because the assembler will only put one or the other on the bus. So I'm relying on the assembler to be able to do that so that there's no human error when it comes down to writing code for this. Okay, so now the pipeline for writing code is you have this fib.asm file. And I want this to be able to include more things. Like, for instance, I want to be able to write dot data, and then have any data that I define in here, like data structures for RAM, or like if I'm making an array and I need to initialize values in an array. I want to be able to write that all in here. What it will then do is it will create another file called like the file name .data or something, who knows. And then it will take that data file, and then I could load that in as a separate ROM that would bootload the RAM. So you turn on the computer, first thing you do is bootload the RAM with the data file. Then now the RAM has all the data structures that you defined for your code, and now your code can access them once it's running. So that's what I'm thinking there. But for now it doesn't have that, so it just does some simple equates, and then for loops it knows how to do loops and labels and assign and count output values and whatnot to actually do the loop. But for here, I don't have any looping functions working on the CPU. I just want to get this to work now. So hopefully, if I run big red assembler and I input file fib.asm, I want to get a listing file, and there's a value, there's an issue. Invalid literal for, why was this working not too long ago? Like it literally generated, oh no, because it overrode it. Let's see here. Does that want to be in? I don't think that makes sense, but okay. Well, input file fib.asm. Oh, I know what I'm doing wrong. We'll go back. This is not going to work. I'll just put in, well, fuck it. Okay, still going to throw an error. Okay, I know what's going on. So what we need to do is run ASM parser first. We run ASM parser, and then we put in fib.asm. Cool. Now fib.asm created fib.jarv here. Okay, and now we run fib.jarv through the big red assembler. Fib.jarv. And now we want a listing file. Okay, cool, different error. What did we do wrong this time? Key error, reg1. Okay, what am I doing wrong here? Oh, I fucked it up here. Save that. So now we have to rerun the parser. So we run the parser and we put in fib.asm. That strips it of all the bullshit, labels all the loops, does all that stuff, removes comments, that kind of thing, converts ASM to this. Now this is correct. Okay. Now I can run that through the assembler as fib.jarv, and I want a listing file. Cool. So now if we open up the listing file, it shows us what happened. It says it converted add R2, R0, R0 into, well, it got me the second register there. Cool. R0, R0. Cool. This looks like it worked. For here, it's saying take the value literal of 1 and add it to R2 and then store back to R1, and then of course it's saying the opcode is 000000000, and the selection bits for that opcode are 1 each to tell it to do add. So you can see here then I got this hex file out here, and what I want to do now is I could say rerun the big red assembler with fib.jarv, and I want a hex file. And now if I go to this, now this is correct here, I can just copy this in, go into here, edit, file, wait, let's see, users, big red, Patreon projects. Okay. Oh, yeah, and then, where is it? Hex file here. So if I open this, I can write in that instead, save it. File, load, fib.hex, open. Okay, cool. And now hopefully, if I run this, oh, we'll get rid of this for now. Okay, cool. No errors. That's nice. So I'm just going to stop the clock and we'll make this not real time, and I'll click it. So we'll clear it, make sure everything's at 0. Cool. So now the ROM is loading in this shit, which looks like it's telling it to do 8. What the fuck is so it's RS2, RS1, RD. Oh, this is 8 here. No, that's 1, 8, 2. Huh. Okay. Let's see if this even works. So if I clock it, we got a 1 coming. No, we got a 0 coming in here. Okay. Is there any 1s on this bus? Yeah, there's 1 and a 0 on that bus. Cool. Okay. So we clock it, and now what's on this bus? 0, 0. What the fuck? Oh, did I click clear? No. Yeah, something fucked up here. Why is it spitting 8 out? Yeah, something's not right. Alright, let's... Oh, all these values are not what got copied in. Control C. Nope, I have to go into this. Oh, maybe. File, save. Oh, I may have to mute myself here for a second, boys. Alright guys, give me 1 second here. My parents are calling. I gotta figure out what they want. Okay, sorry about that. We are back. Alright, I gotta boost my mic again because every time I lower it, it fucking fucks up the audio properties. Put it back to 6 dB. Hopefully that's good and it's not screaming in your guys' ears. Okay, so what I wanted to do is check this. Yeah, see, this is wrong. This is not the right value. So we want to load this. Why is it starting with 8s? What the fuck? Okay, let's go back here. Let's look at the listing file and see what's going wrong. Okay, so we got 1 0, 2 zeros, 3 zeros. Oh, we got a lot of zeros. Let's start from this side. 0, 2, 1. Oh, no, okay, because so it's saying this is a 4. So it's saying it looks like that. which should make that look like a 2. Shit. Yeah, so this should be right here. And it should be 4 plus 3. Let's do it right here. Calculator. Decimal. 4 plus 3 plus 6 plus 6 plus 6 plus 32. 57 bits. And that's what I told it in here. 57 bits. Okay. Okay, you know what we'll do? We'll go to fib.hex. We'll load this. Go to edit, file, clear, file, save as fib2.hex. Okay, now that we have a blank file in there, we can pull up. Why did I close it? This PC C, yeah, I know it's basically used up. Users, Alex, PyCharm projects, Big Red. Alright, so we have fib. Oh, why did I go to, oh, no, okay, no, so we want to be in users, documents, Big Red, users, Alex, documents, Big Red, there we go, edit, paste it in there. I think it needs that bullshit v2.0 raw bullshit. Alright, so now I save this, minimize that, won't exit out, edit, file, load. So hopefully if we load fib, there we go, now the values are updated. Okay, okay, save. Okay, so now if we go clear, clock it, turn off the clear, so now what should happen is we should have Fibonacci on this bus here. So 0, 1, 2, 3, 5, 8, whatever. So we could stop it, and what I can do here, just really easily, I'm gonna have to go in a few minutes here. Components, outputs. What the fuck is that thing? Sounds like a big ass truck outside. Anyway, so now we're gonna go here. We're gonna give it 32 data bits, and we're gonna say it's a decimal output. Okay, cool. So now if I run it, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. So whatever, that's Fibonacci there. And then, oh, it didn't overflow. I just don't have any more iterations in the code there. So we can go several more times before it overflows. And then we can clear it and, you know, step through it again. So anyway, there we go. We just proved that, you know, this is, you know, somewhat on our ways to a CPU because it's able to control the buses in a way that it's able to get it to generate add instructions. Now obviously I can also now multiply inputs by using the add instruction, but in the assembler it's going to use the add instruction with the multiply enable register. It's going to be interesting. It's going to be, yeah, I don't even think I need this multiply. Like, I'm going to have to go in here and edit this because I don't need this multiply control line coming out. Actually, no, I'll leave it. Yeah, no, I do need that, and then it'll be encoded as an arithmetic operation on the ALU bus, kind of. Yeah, it's going to be interesting to figure out how I'm going to actually get that working. But yeah, so there's Fibonacci running on it. And now it's real easy to now assemble the rest of the instructions whenever I want to do that. Is the stream still on? Stream is still live. Okay, cool. We haven't lost it yet. I hope the quality is good too, because I had to lower the bitrate a lot to actually be able to to stream because it was cutting out last time when I had the bitrate set so high. Yeah, so now what else do I need? I could write a test instruction, like write test instructions to test the outputs here, what they should be. So I could put like 5 and 3 on the inputs and then do all the arithmetic, logic, and shifting instructions and see how they turn out. And then I could try and multiply maybe, but then that means I'd have to write the assembler to do those instructions. So I guess if I'm going to do anything more, I should write the rest of the assembler out, which isn't too bad. So we can come back over here. Yeah, so what we can do is, this is basically a template for most of what I want. There's not every instruction in here that I want because my other, what I took this from didn't have them all. The only thing I have working right now for this new one is add. So now if I want to get, I will remove all of these other arithmetic ones, arithmetic and logic, and I will now implement them all based off the add here. The other thing I want to do is see if this still works. Run fib.jar listing file. Cool, okay. And it didn't raise an error because the immediate value was not larger than that. Cool. Okay, so now what I'll do is I'll just copy this. So, insert, I don't know why that was fucked up. Okay, so now what we're going to need to do is pull up the instruction set architecture. And so now the arithmetic is able to do add vector, subtract, and absolute value. So add was opcode 0 select 1. Now we're going to have opcode 0 select 2, and this is add vector, add v. And everything else stays the same. Wow, that was real hard, right? So now we'll go to the next one. Paste it in, move it down one because it looks weird. And now we'll have subtract. And now we can have select is equal to 3 for subtract. And now we can have ABS, absolute value. Now ABS only, now this one is tricky, right? Because we're only taking the absolute value, it's a unary operator. So since it only takes one value, we need to subtract from here this. And then therefore it's getting the destination and the source. So because of that, it's getting destination and source 1. Therefore it doesn't need an RS2, right? So that means what we want to do is kind of get rid of this here. Rename this to RS1 instead of RS2. Then bump down all the values in here. So this would then be arguments 2. This would then be convert to arguments 2. And this would then be arguments 2, right? Because the first thing that you're going to do is you're going to get the 0th thing is the absolute value instruction. Then the first is then going to be the destination, and then the third is the source. What are you taking the absolute value of? And actually, it would never even make sense to take the absolute value of an immediate. Like, why would you take the absolute value of an immediate? But you know what? Fuck it. It's there if you want it. It's just you'll never really do that. Like, why would you take the absolute value of an immediate instead of just putting in the immediate value with that absolute value already taken? Whatever. We'll leave it. Okay, so now we have all the arithmetic done. I'll take out this control. We'll control C this. Do this. And we'll build a new, oops. Alright, so those were our arithmetic instructions. Now we're going to have some logic instructions. Okay, so now we have to look up instruction set architecture. Now, from arithmetic to logic, all that increments is opcode, and everything else decodes the same way. There's no change in like the format for instruction. So because of that, now we just have the logic select table. You know what? I'll write a comment in here to explain what gets done. How about that? Hashtag. You can tell I don't use Twitter because I can't find the hashtag very quick. Hashtag arithmetic select. Hashtag 1 add 2 add vector 3 subtract 4 absolute value of a. Okay, and then arithmetic select, and then yeah, I need to put opcode hashtag opcode. If I could spell opcode is equal to 0. Okay, there. And now I'll do the same thing down here. But the opcode is now equal to 1. And the logic select is 1. Okay, well first off, we change this to logic. 1 is and you can see I don't start at 0, because if I did, then every single one of them, when there's no data in there, will be out doing a logic operation at 0. And that would be bad. Five is then XOR shit. 5 is XOR. 6 is XNOR, and then we fuse them all up. And the opcode is equal to 1. Oh shit, did I fuck this up? Oh no, 1 is AND, 2 is NAND, 3 is OR, 4 is NOR. Okay, cool. And now we can just bump that down a little bit, copy a standard arithmetic op. Now we're going to change this to AND, where opcode is 1, select is 1, everything else stays the same. And now this changes to select 2, and we'll just increment through this as we go. NAND OR should then be select 3. NOR, I think, if I did OR above, right? So OR NOR, yeah, so NOR is 4. X OR is then 5, and then X NOR is then 6. Cool. Okay, so now we have the logic instructions. Yada yada yada. Okay, now with the add instruction, or up here I guess in the arithmetic selection, no, fuck it, I am gonna have a multi instruction, yeah. Yeah, okay, so okay, so I need to shift all this shit down. Control X, Control V, add, Control X. Sorry, I'm doing this on a different page. I guess I can drag it over. Okay, so what I'm doing here is I'm modifying this. I want a mult instruction. And what mult will do is literally just it would force you to have a value larger than 31 that is even in RD. So RD has to force you in the assembler to be a multiplication register. And then source 1 can be any register you want. The low or high of a multiply register, a low or high of a multiply register, or just a general purpose register. RS and R1 and RS2 do not care. The reason I need to do the mult, I need to have a dedicated instruction for it, is it needs to know the flag out of here to enable the multiply to be used, to be written. Oh no, wait, no, it doesn't. Yeah, it'll be another like fallback select. It will force in the instruction decoder to have the mult be true to allow the multiply right back to go there. So even if the assembler somehow does end up putting in instructions where it doesn't mean to use mult, maybe I'll go through and force all the arithmetic, logic, and shift instructions all to be low. No, I can't do that. No, I could force the results, the RDs to always be, force the RD to always be less than 32 in all the arithmetic logic, and force the RD in the multiplication to be above 32, or 32 or above, well 31 or above 31 I should say. Yeah, and I don't, shit, so I don't think I'm going to need anything in there. We just need to force RD to be above 31 and even, so divisible by 2. And then here we just have to force our, I don't know. The assembler will just have to be, oh, in the assembler I could, yeah, okay, I keep saying the assembler. I have to write the assembler, Jesus fucking Christ. Shit. Let's play some more music in 1 second. Okay. Hello, whoever's still viewing the stream. Okay, this needs to be changed to a 57-bit instruction. Because we have 18 plus 32 is 50, plus these 4 plus 3 bits is 7. Okay, so the multiply instruction will be, alright, I guess I haven't even gone through and done the shift instructions. So that's one thing we can go back and do is compare arithmetic, we did logic, and now we need shift. Shit. I hate how it does that. Alright, shift is going to be opcode 2, and then we have the shift select here defined. So opcode 2. And I'm just going to move this back to my other screen. Okay, so shift select 1 is going to be shift left logical, 2 is going to be shift right logical, and 3 is going to be shift right arithmetic, and we don't have a 4. Okay, so now we should just be able to copy this. Okay, so now we're saying shift logical left when opcode is 2 and shift select is 1. Cool, and the shift amount can either be an immediate or a register. And now we're going to have shift right logical, and the only thing we have to do is increment select to 2. and then we're going to do the same thing and then just change it to 3 and make shift right arithmetic. Cool. No, okay, Sam, so this one is definitely not meant for Minecraft. It's a 32-bit CPU, and it's got a hardware multiplier right next to it, so I'm hoping to simulate this at a megahertz plus, and then that'll allow me to actually do like cool stuff with like drawing frames and like trying to actually render stuff. I'd like to be able to control a 3D render engine with this, to be honest. Like, I saw like a ray tracer done on an FPGA. I thought that was neat as hell. So I would love to be able to like make the CPU good and fast enough that it could like run a hardware ray tracer unit on the output. That's why this is my first CPU where I realized like I can have DMA, direct memory access, and instead of controlling everything through a port, the DMA is set up through the port to access the memory that it wants to access. So for instance, 3 output ports are used. One is a offset, one is the base. So you have the base, the offset, and then you have how much to count by. So you say my base is like, say, address FF in RAM, and then I want to offset by 1 because I'm loading bytes. If I was offsetting by 2, I'd be loading halves. If I was offsetting by 4, I'd be loading words. So let's say you wanted to load bytes from, actually make it more accurate. Let's say I wanted to load halves from address FF to load my memory, because like let's say I had 16-bit RGB or something like that. Or if it's really 15-bit and the 16th bit is 0 because it's 555 RGB. So I could load 2 RGB values at a time by loading a word, or I could load 1 at a time by loading it a half at a time. So depending on what the I/O device wants to do and how it interprets the values, it may load a word, it may load a half at a time, and it's up to the I/O device to request that. So it's it's up to either the if it's an input device, it's up to the input device to request what it's going to write by, and if it's an output device, the CPU tells it what it's going to write by. That kind of deal. So this is going to have direct memory access, where, like, say the terminal can be written to sequentially. It just can load. It can request, you know, however many bytes or words or whatever from RAM address XX to YY. Or XY to ZW, whatever. And doing that will allow you to then have it be really fast. So it could just, and when the DMA controller will take control, the CPU will stall. When the DMA controller gives returns the RAM bus back to the CPU will continue. So that's kind of how I'm thinking that will work. So yeah, we just did the shifts and what do we do? Shifts, logic, and arithmetic. Okay, so yeah. So now what we can do is make a copy of this. How do I do that? Oh, copy. No. New file, test file .asm, or no, we'll just call this test.asm, and we will just, for ease, do this, and then get rid of whatever's inside. Alright, so I'm not going to actually have any directives, and I'm just in the code, I'm just going to hard code everything. So we're going to say, we're going to test all sorts of instructions here. Let's do add. We want to store into add, we'll say R1, and then plus R0, and it's going to get 0x 05. Hopefully that'll convert to the right value. I'm curious because I don't want to type in all the zeros that I need there. So 0, maybe I could just do 0x5 like that. And then for here, maybe I can do add R2, R0, 0x3. Okay, and then now what we're going to do is we're just going to do results on this that we're going to... I guess we could write them back, but I don't plan on using them. So we could say write a comment here that says, this is now testing all ASM ops in the assembler so far. Okay. So now we could say, so obviously we tested that, so now we're going to say like add R3, R1, shit, R1, R2, so that should now generate an 8. Now we're going to say add, write it back to R3 to, I don't really care about using, like, what, I know the registers get written back to, I'm not worried about that. I just want to test that it generates the right values on the output. So now we're going to do add R1, and we'll do an immediate like 0x1. So if R1 is 5, it should now go to 6. Okay, but now we have a lot of instructions to test. So now add vector. Let's generate some higher. So we'll use R4 to write this back. No, we'll worry about that in a second. All right. So now what we want to do is I want to test that the add vector works. So I want like 16 bits. I want 16 bits low and high in a register. So like for instance, I'm going to just end it. What I'm doing up here is basically like load immediates, but they'll be pseudo assembled into that. So I'm going to use register 5, I guess. Even though register 4 is available, I'll skip one. Register 5. And I'm going to add 0 plus then the immediate of 0x 1, 2, 3, 4, 5, 6, 7, 8. Okay, so what do I want in here? I want to have in the low, we'll do 0, 1, 0, 1, 1, 0. And in the high, do actually no, we can leave it as FFFF, and then we can do this as 0001. Okay, so that'll be the 32-bit value that we load, and then what I'm going to do is I'm going to -1 from this, and I'm going to add 1 to this using the add vector operation. So how am I going to do that? So I can split this into 2 vectors, one of a low 16 bits and one of the high 16 bits, so low and then high, like this. And what I can do then is say add vector. I'll write the result back to R7 just so I can skip some and have some reserved to myself. And now I'm going to say add vector. And now the 2 things I'm adding, well obviously it's going to be R5 because that's holding this value. Oops. So we're going to write R5. And now I'll use an immediate and I'll -1 from the top, so that means add FF to it, so FFFF, and I'll add 1 to the bottom by doing this. So by doing that command there, the top portion will become FFFE, and then this will become 0010. So I'm just going to -1 from the top and add 1 to the bottom, which just happens to be doing the same thing to itself. Okay, so now we have add vector. What else do we have? Subtract. Subtract, we'll store back to R3, and then we'll do R5, R1 minus R2. So source 1 is R1, source 2 is R2. Then we could do sub R3, R1, and then if R1 contains 5 and we then do 0x1, that should then subtract 1 from it. So if this creates 2, this should then create 4. Okay. Now we need absolute value. So if we take absolute value, now we can take the absolute value of 5 because it's got a 1 in the most significant bit. Alright, so let's say take the absolute value, R8 gets the result of the absolute value of R5. Alright, we'll make a comment, hashtag testing arithmetic ops. And now we're going to say testing logic ops. Alright, so this is going to then become and. So we're going to and R1 and R2 together, which is 0 and 5 and 3 should create 1. Then we're going to and R1 with 1, and that should also create 1. So these should be very predictable results, hopefully, as we go through this and test them all. Okay, so now instead of and, we have NAND, so we'll just put the N in front. But other than that, we're keeping the structure the same. So now this will be OR, NOR. Oh shit, no. This would be stays OR as well. Then this becomes NOR. And then I guess I can use this. Oh, actually, what we can do is just do this. And just put X's on the front. Cool. Alright, so that's logic ops, and now we're going to test shift ops. We'll save the file just in case. Hi, would you like to know what... I would like to know what software you're using to design circuits. So the software is actually called Digital. I can send a link. That's the software. It's quite fast. It's a lot faster than Logism, and it's still maintained, and you can actually talk to the dev. So much better in my opinion. So now I need 3 sets of instructions. This is going to be shift left left, or shift logical left, shift logical left, shift right logical, shift right logical, shift right arithmetic, shift right arithmetic. And we're going to say R3 gets R1 shifted by R2 amount, and R2 is 3, so we're going to be shifting by 3. We're going to be shifting 5, either 3 left, 3 right, and then the arithmetic shift, I want to use R7 on the arithmetic shift. And we'll say shift right arithmetic 7 by 3, or shift it right by 1. Okay. This should work, and this should assemble. You know, I hope so. I should comment hashtag define constants. Alright, so now we run this test.asm, should be fine. Okay, so now test.asm, I'll get rid of all the fib files. Test.asm created this file, test.jar. So now if we run test.jar through, I want to get a listing file, see what happens. What did I have an issue with? Alright, I'm curious if it's just the small immediates fucking with it, and if you gotta type them all out. So, easy way to test. Yeah, it looks like that's what's happening. So if I want 32 bits, 1, 2, 3, 4, 1, 2, 3, and now if I run it, test center. Huh. It says an issue down here. What? So it's telling me 1, 2, 3, 4. Yeah, that's a 32-bit value. Add R0, R1. What the hell? Hex int of. Okay, what if we just run test.jar? Let's get a binary. Okay, it does. Oh, no matter what I do here, it's not gonna like. Why can't I convert instructions to base 2 and then take the hex of that? Does instructions need to be? Yeah, I don't think that's what needs to happen. I think I'm missing something here. That used to just work. Yeah. Oh, no problem, Max. What the fuck is going on here? Hex list, it becomes print instructions. Run test. It didn't even print the instruction. Print instructions. Why didn't it print that? Oh, because there's nothing in instructions in? Oh man, what the fuck's going on? So in this, what is this function called? ASM to int? It does all this shit? Yeah, ASM to int is this function. So when we run, we're taking the current line, and this ASM is returning the binary instruction. It's returning binary instructions. So I want to print LST here, I believe. Run fib.jar. Oh shit, I'm running the wrong thing. Shit. Test. Okay, so what I got out was add. So print ASM print print instructions list. Okay. So there's nothing in instructions list. What if I just comment this out and rerun this? Test.java. And created that listing file, which didn't do any conversion. Why didn't it do any conversion? Did I mess up the indentation somewhere? Yeah, what the fuck is going on? Huh. So test.asm goes through the parser, creates that, and now that goes through the assembler and should create a binary file, but why isn't it? Alright, let's see if it generated binary. It did not. Is this just over the size that it can? I don't know if this is just over the bit width that it can return here. To be honest, this is throwing me for a loop. Oh, it's thinking of it as a comment? Huh? So we have opcode select, RD, RS1, RS2, immediate. So I can say print binary instructions, run test.java listing. It's like got nothing in there. It's not printing anything. Yeah, see how it's not printing anything? It's not even getting here. Did I fuck up with add? I probably spelled it wrong or something. No. Add arguments does not equal to 4. 1, 2, 3, 4. So it should then then I should be able to say print opcode select RD RS1 RS2 immediate. Test. Okay, so we got opcode of 0, select of 1. Okay. Okay, so why won't it print? It won't print this here. Oh, it's just going to this else thing. Why does it think it's a comment? See, it's just returning blanks and the input file. What the fuck? Oh, should this go? I don't know if I should do that. Let me check my other assembler, I guess. What is the order for it? Else binaries. Yeah, this should be it. But for some reason it's just returning this. So if I comment out this test.jar listing file. Yeah. It was thinking it was, for some reason it was thinking it was something else. I don't understand why. But now I can test if it cares about this. I can run this again. Test.jar listing file. It does not care. Okay, cool. So now if I run this and input test.asm, cool. Now test.jar should be fixed. Now I should be able to run this. Test.jar listing file. Oof. Oof. Okay, yeah, so I gotta get rid of this statement. At least on the ads. Let's see if this will run now. Oh, I need to do it on the ad vector as well. What else do I need to do it on? I'm not using large immediates on anything else. You know what? Here's what we can do. Just get rid of that line on all of them. God, this sucks. Oh, I guess I can get rid of, because this isn't working for my CPU, so no need to have it. I kind of want to leave those so I remember them. Okay, so let's run. Fuck. Test.drive. Oh, okay, so the other thing I can do is say it doesn't need a print. Okay, what the fuck? Oh, because I'm telling it. That's right, okay. So one thing that sucks about this is you can't say what this, we have to convert this to, let's see here, calculator. We have to convert this to toScomp, right, because that's a signed value. And that's then too big for a signed value. So you have to tell it what it is negative-wise. So if we say invert that and add 1, we get all zeros there and a 2. No, wait, no, never mind. Let's hex enter 1, 2, 3, 4, 0, 0, 1. No, go to binary and do bitwise not. And that's equal to wait, what the fuck? Alright, I'll just do it by hand. F 0 0 0 1, and we invert all, we get 0 0 1 inverted goes to 7, or goes to 14, so E, C, D, E, F. That becomes E. That becomes F, 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 and this becomes 0, 0, 0, 0. And then we add 1 to that, and we get 0, 0, 0, 0. That carries a 1, 0, 0. No, it doesn't. That stays 0. 0, 0, 0, 0, F, 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 F. So if we take the 2's complement of that, and we just say that's negative F, 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 that should work. So we say negative F, 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 F. If we run this now, test.asm, run this. Now test.jar here. Oh fuck. So we need to say negative F, 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 F. Run test.asm. Run this. Test.jar. Now this should be fine. The listing should. And now if we look at the listing file, you can see what negative FFF got converted to. It got converted to what we wanted right there. Okay. So now that I didn't have a spaz moment, so load immediate will have to recognize this in the assembler and will know to do the 2's complement conversion for you. So you can actually put in, so when you do a load immediate, you can actually put in what you want and not have to think about it. Okay, so now that that works, we can run this again. Well, actually, I can get rid of this. Run this. Test.jar and generate a hex file. Oh, okay, right, because we were having issues with the hex output. So we will undo that, and we will undo this. And the reason we're having issues is because there's nothing in there to do, because we were having issues further up the pipeline there. So test.jar. We want a hex file output. Beautiful. And now if I load that hex file, we got, oh, wrong thing. We want test.hex. Boom. Got test.hex. So now what I can do is load this file here. File save as test.hex. And we'll do an all file save type and save. Okay, cool. So now, when I come into here, I should be able to edit, file load, test.hex, open, boom, we have 18, 19, 20, we have like 32 instructions, really? 27. 4C31 should be the last, yeah. So we have 0, 3, so 4. Oh, so that's dumb of me, yeah. That's really dumb of me. I rolled over. So that we have 16 plus 8 is 24, 25, 26, plus the 0th is 27 instructions. And that's what it says we have here, 1 through 27 is 27 instructions. Cool. So that is right. Okay. So now if I pull up the assembly code in another file. So the first three things it should do is generate 5, 3, and then the FFFF0001 value on the output here. So what I will do is we will copy Control-C, Control-V, and we will make this signed. Okay, so we'll have decimal, assigned decimal, and then we'll also have hex. Oh wait, no. We'll just leave this as decimal, and then this one as hex. So now if I run this, clear it. Okay, so now we enable it. So the first thing we have coming out is 5. Cool. Now we have 3. Now we should have negative FF, yada yada. So that's what we wanted there. Alright, so now it should add 3 and 2 together, or 5 and 3 together to make 8. Cool. Okay, so now it should add 1 to 3 and make 4, I believe. Or no, 1 to 5 and make 6, okay. Now it should take and of the first 2 and make 1. Oh, we're doing add vector, sorry. So it's doing add vector, and therefore it should have subtracted 1 from here and added 1 there. Perfect. So that's the add vector instruction. Now we're going to subtract R1 minus R2, so 5 minus 3 should get us 2 on this. Yep. And now we're going to do one of those numbers minus 1, so I don't remember which one it is. Okay, so we did 5 minus 1 and got 4. Okay, now we're going to take the absolute value of that negative FFF value, and it should spit out FFFFF, obviously. Oh yeah, it spits out, yeah, FFFFF0001, because we put in negative FFFFF. Cool. There's the absolute value instruction. And you can see that the arithmetic select here is set for 2, which tells it to do absolute value. Inside of here. Okay, so now we can test the next instruction, which is going to be AND. So this should produce a 1 on the output. This also should produce a 1 on the output. Nice. Now we're doing NAND, which should be inverse of that. So this should be all, all zeros, or all F's and then a 0. Yeah, or then a 0 0 0 1. Or 1 1 1 1 0. Sorry. Yeah. There you go. And this should be the same thing. Now OR is going to be 7, and this should be the same. Oh yeah. We take OR 5 and order it with 1, so then we've got 5. Then we're going to do NOR, so it should be the inverse of all that. Cool. Now XOR should be like 9 or 6, yeah, and then I'm just XORing a different value, and now it should be like 9, yeah, at the end, and then this, the inverse of 6, which would be B. Okay. No, I thought that would be 9. Whatever. And then now we're doing shifting. So we're going to take R1 and shift it R2 amount of times. So we're going to take, what is R1? R1 is 5, and we're going to shift it 3 times to the left. So that should be like 5 goes to A, goes to whatever, shift to 20 something. So 28. Okay, cool. Yep, that works for me. So what we did is 5 left shifted 3 times is 5 times 8, which is 40, which is another way to check right there. Okay, now we'll do 5 shifted once to the left, which should be 10. Yep. Okay, now we're going to do 5 shifted 3 times to the right, which obviously should then just be 1. Oh wait, 5 shifted 0. Okay, yeah, 0. We're shifting it out we're not just shifting it twice, we're shifting it 3 times. Okay, and now we're shifting it just once, so we should have a 2. Okay. Okay, now we're doing shift right arithmetic. We're going to shift that big negative number right, and it should FFFF0001. All it should do is bump out that 0001, but leaves the F's. Oh yeah, and then it bumped right. Yeah. Okay, yep. 0001, and that becomes bumped over by 1 bit. Okay, so that becomes C. Shouldn't that be 8? Whatever. Oh no, because I'm moving it 3 times, not once. So yeah, that makes it C 14, which is C. No. Whatever. And now we'll just shift it right once. There we go. So, oh, we can't open up that circuit while it's running. Yeah, and so that's us testing out so far every instruction that we have built in. What do I have set up for them? I have multiply as the 4th op. Is that what I left it as here? Multiply is the 4th one, aka 0 to 3. 0 to the 3rd one is obviously the 0 through 3 makes the 3rd one the 4th one, obviously. So. Okay, so I could, in theory, run a multiplication, I guess. but there's no mult select needed. It will just, the assembler will encode it as an arithmetic select, I believe. No, it doesn't need to encode it as anything there. It doesn't need anything in the select bit. It will literally do nothing. All that the assembler has to do is encode it as a multiply operation, which has op3, and then force RD to be above 32 and even, or above 31 and even. Yeah, so I think that I'm going to end the stream here for now. Hopefully it's still streaming, I don't know. We'll find out in a second here, I guess. Yeah, it looks like we're... Oh no, I got some viewers. No, maybe I'll stick around if you guys are actually still watching. Okay. I mean, I'll have to go in a little bit still, but... Okay, so what I guess I could do is I go back to the assembler, and we can fix the multiply. Okay. So I don't know if I even included it in here. No, I didn't, but the multiply operation will be, I guess, underneath the shift. So we'll just call this shit. Multiply. So the opcode for multiply will then be 3. And then the multiply select, just not applicable. So use 0. Okay, so the multiply select isn't going to really mean anything in this instruction, so there's going to be nothing there. And all that we want to do is an hashtag force RD must be greater than 31 and even. Okay. Okay. RS1 can be anything that we want there. Oh, and we ran out of music. I'll pick a new. Okay, so what I want to do now is just basically grab the add instruction. Okay, so this is going to be, I don't know if I want MUL or MULT. I think we'll leave it as mult, like that. So the opcode here has to be 3. Select has to be 0. Okay, now RD here. Now we're going to say if RD is greater than 31 and RD divided by 2, modulus 2 is equal to 0. Does that work? If RD is greater than 31, so I need to convert, I need to grab it first here. Then it can, then it can go on to the rest of the shit here. Then we say else. How do I raise an error? Oh, I threw that away. I got rid of all that. I want to raise. I don't know. I don't know. I'm just making up random error numbers at this point. I don't even know if it'll print it. We're gonna say RD is not a multiply destination register. Okay. So it says that's invalid syntax. So let's see here. Anybody got any advice in the comments? Guys, I gotta look this up. Python if statement modulo. Python if statement and operator. If RD is do I need that? I don't know if the spacing matters. Oh, duh. Oh, thanks, Sam. Input file, there we go. Test.jar. Listing file. Cool, it worked. Okay, because I didn't do anything fancy. But now let's try this. Okay, so now we're gonna test. Yeah. Thanks, Sebastian. I realized that. So then we're gonna test molt. So I'm gonna say molt. Now we could say the result can be M0. It's an even register that's defined as a multiply register that when it gets converted back will be converted as register 32. And what do I want to multiply? Let's multiply R1 times R2, which is 5 times 3, so we should get 15. R1 R2. Okay, now this should work. So if I save this, run it through the parser, test.asm. Fine. Now we take test.asm, which generated test.jar, and put that down there. Now we run this. Test.jar. Should not throw an error. Cool. So now since it worked, I will. Okay, so now that I know all these instructions work, what I'm going to do is I'm going to go back to my file here, create a new file, rename it test molt, I guess, edit, get rid of all this shit. Okay guys, I'm going to have to go. It's good streaming with you, but yeah, I have to go. I hope you guys like and enjoy the stream, and then don't forget to subscribe, and then also you can join the Discord in the comments. Anyway, thanks for watching. I'll see you guys next time.